pleasure to introduce to you Professor Geoffrey West. Geoffrey is a distinguished professor from the Santa Fe Institute in New Mexico. He's been rewarded by Time magazine as one of the most influential thinkers of our time.
So here's the title of my talk, and what I'm going to do is give you a very broad overview of some ideas around complexity and transdisciplinarity. And inevitably, those kinds of problems clearly require a multi-transdisciplinary kind of approach. What is complexity? How do we define complexity, et cetera, et cetera? And this is an ongoing issue. Okay, so the other issue that comes up when you use the word complexity is, of course, what do we mean by complexity versus simplicity? So here's an example of what I mean by simplicity, the solar system. We know that we can describe that with extraordinary precision using Newton's laws of motion, Newton's laws of gravitation, the motion of the planets, the motions of the various bodies in the universe to a great degree can be understood from very simple, basic, universal laws. I can write down on one sheet of paper the equations that describe the motion of that. That is in marked contrast to something that I'm now going to focus in on, and that is a very important aspect of complexity, that it is scale dependent. Because indeed, even though we think of this as, quote, a simple system in the sense I described, if we look at these various planets and we focus in on ours, we see that on ours there's certain structure, which we easily recognize. And as we focus in on that, as we make the resolution finer and finer, we start to see more and more complex structure. And if you look fine enough, you see that. Now that, in terms of the way it's functioning, in terms of the extraordinary dynamics that is going on in that forest, in that ecosystem, not only the things that you can see, but all the things you cannot see that are going on there, the interchange of energy and information that is going on there is complex, because I would, instead of writing down on one sheet of paper, I would need a book probably as big as this whole building, maybe even bigger, maybe it's even impossible. We know that system is complex when we look on this planet. That system is also complex. That's another. And one of the questions we might want to ask is this complex system actually just another version of that complex system? Is in fact the dynamics of that city somehow related to the dynamics of that city, even though we call that a forest? So there's a scale problem, there's problems of networks, then here's another net, that happens to be Manhattan, and then there's problems of scaling of the economies of these networks. There's a brain, there's a cell, all of these are highly complex systems. There's the economy and the markets. So all of these come under the same kind of rubric, and the question is, can we attack these as serious science problems? Can we understand them? And is there a way of thinking about them that is more holistic, more integrated? The last example I'm going to do, and I'm going to spend 2 minutes on this, a little bit longer on this, is airplane manufacturing, because what this is the breakdown of the Boeing 787, the new Boeing 787. Now, what does that mean? That means that there's an extraordinary network that was built up by Boeing unwittingly. They didn't even realize they built up this extraordinary global network, and they treated it as if it was still all in Seattle. They built up a network that has all kinds of sensitivities to small changes. So some small change that happens in Wichita may actually propagate through and affect something in Winnipeg, that affects something in Nagoya, that ends up affecting something in the assembly in Seattle. And what did that mean? That they had built up a complex network system. And in fact, they built up a complex, evolving, adapting complex system. One of the messages I want to leave you with as I go through all this, when I come back to, and I will discuss more of complexity, is the following. One of the things that you discover in a complex system, and is represented by what's written here, and indeed you are very familiar with this, that if you don't consider it that way, you risk collapse, as I think the example of the mortgage industry in the United States, which is a tiny piece of the United States economy, almost brought down the United States and brought down the global economy. The second lesson is that given that, I believe we need a new paradigm, a new integrated conceptual framework that is systemic, holistic, to deal with these kinds of problems. And that's the great grand challenge for the 21st century. And finally, the other point I want to make is that the acceleration of the threat to sustainability, the one that where we feel that all of these problems that are the ones I listed above, that all of these suddenly seem to be hitting us at the same time. The case that I will make is that that is all because of the faster than exponential growth of urbanization. When the United States was found, less than 4% of the US population was living in cities. By 2050, 80% of the planet will be urbanized, and last year, or the year before, depends how you count, half of the world's population now lives in cities. And this is happening at a super exponential rate, and all of the problems that we're facing are all generated by cities, all of them. I'm going to slip through here to just talk a little bit about some buzzwords of complex systems. Just to remind you of some of these, you're familiar with most of them. They obviously contain huge numbers of individual actors, components, sometimes modular components, and so on. They typically cover many different spatial and temporal scales, different time scales. I just showed you, the simple example I gave at the beginning, if you think of the planet, at one scale it just looks like a billiard ball. It's a sphere. At another level, it's a bunch of forests on land and sea and so on. At another level, it's a bunch of cells. The interactions are highly nonlinear, typically. And that leads to all sorts of other consequences. One is the one I've already mentioned, tremendous sensitivity to boundary conditions, like the mortgage industry triggering some tiny effect, like the mortgage industry problem in the United States, triggering a global phenomenon. Out of these multiple scales, we have these emergent phenomena. That is that, for example, a city, which we just talked about, is not just the sum of all the people in it. It's not just the sum of all the roads or the sum of all the buildings. It is something more. They are typically historically contingent, and there are often accidents that happen that determine their future. These systems are extraordinarily robust, and the robustness... Does it come? Good. The robustness depends a little bit on your point of view. The system that we've created, that is, the social system that we have created is probably almost certainly, in my opinion, is almost certainly not robust in the scale of thousands of years. It might be 10,000, 20,000 years. It might be robust over hundreds of years, but on long term, it's highly unlikely that what we have is robust. Nevertheless, human beings acting in communities is extraordinarily robust. Life is extraordinarily robust. So these systems are, that's part of being adaptive and evolving. They're usually not in equilibrium. That goes again along with adaptive and evolving. And I've already emphasized this difference between complicated and complex. And the last thing I want to emphasize, which is a question mark, but is often true of these systems, despite the extraordinary diversity and complexity that we see in a complex system, whether it's a company, a city, a cell, a brain, there is often a remarkable underlying simplicity. And indeed, it was the discovery of this in many model systems that led to people beginning to realize that maybe, despite the fact that when you start to look around you at these kinds of things, they look awesome in trying to attack. Nevertheless, first of all, with simulations, computer simulations, that very, very simple rules led to extraordinarily complex behavior that gave credence to the idea that maybe we can understand some of these systems.